Our first talk, Brian will be giving on behalf of his team at Kitware and maybe some other collaborators. His talk's on explaining model robustness, combining saliency maps and natural robustness testing. Brian.
Okay, cool. Thank you. Yeah, so my name is Brian Pugh. I'm a researcher at Kitware. As Nate mentioned, we're looking at kind of combining these two generally kind of independent lines of work. So kind of model robustness along the test and evaluation front, and also kind of model explainability. And this is joint work with others at the team. So one quick slide about Kitware. So we are open source software R&D company, and we do a lot of work in computer vision. These are some of the main areas that we work in. The talk today is mostly going to be covering kind of AI test and evaluation stuff, and also some explainable ethical AI. If you're interested in learning more, you can visit the website. So the outline of the talk, I want to do a quick intro into some of the current work that the U.S. government Department of Defense is thinking about in terms of AI assurance, and then talk about a very high-level introduction to natural robustness testing, so a way to test models against different risks, explainable AI, and why we care about that in this context, and then show how this framework could be applied to one example use case, which is satellite image classification, and then kind of have some summary conclusion. So in general, AI test and evaluation, the U.S. Department of Defense cares a lot about this. In 2022, there was this responsible AI RAI strategy implementation pathway that was put out. It called specifically for the need to develop new AI test and evaluation tools, and to make that available DoD enterprise-wide to support various testing operations. And then part of this effort, one of the programs that came out is this CDO JADIC program. So CDO stands for Chief Digital AI Office. JADIC is the Joint AI Test Infrastructure Capability. So it's a program of record. It's funded for 5 years or so. There's a large investment in kind of the AI community ecosystem. And the main objective here is to develop software to accelerate and enable AI testing and evaluation for DoD testers to provide insight on the effectiveness, robustness, and safety of the DoD's AI-enabled systems. And so as part of the JADIC program, there are a lot of different software tools that are being developed, things that cover stuff like adversarial robustness, data set analysis, data set quality. We are specifically focusing on explainable AI, a toolkit that provides various explainable AI techniques, as well as a natural robustness toolkit, which is meant to facilitate model robustness testing. But you can see that there are other tools here as well. If you're interested to learn more, there's a public-facing page that describes the goals of the program and the other tools. So I encourage you to visit them. And then in the following, I have one brief slide about each of these tools that we'll be using for the current work. So the Natural Robustness Toolkit is a platform for generating validated sensor-specific perturbations and transformations to evaluate model robustness. And so here, the diagram shown here on the right, this is the typical training framework where you have a model, you might have training data, validation data, test data. You use the validation data to tune your model, and then eventually the test data to measure performance. What we're interested in here is really expanding that test data. The test data is limited, it might not cover all of the factors that you would care about. So expanding it in meaningful ways to provide a more expanded test data and a better measure of whether your model is robust or not. And so we'll show how we can use that here, but the main takeaway is that NRTK helps with expanding existing data sets to enable more robust testing evaluation. And then explainable AI toolkit, it's a platform for currently really focused on visual saliency algorithms, but these are algorithms that indicate in the input image or input data what features the model cared about or used for its prediction. So the XITK provides these different algorithms, and the goal is to really enable better human understanding of these complex machine algorithms. So this is a tool that was transitioned out of the DARPA Explainable AI program. Okay, so to provide some motivation, so here we're interested in taking these two tools and then applying it to a standard test and evaluation workflow. And so here we're focusing on two different types of image perturbations. So one is Gaussian blur. This corresponds to different real-world effects, such as camera focus. And then we're also using salt noise, which could be modeling kind of sensor-specific noise. And then I would say that the framework is agnostic to what types of perturbations there are. We can use different ones, but these are the ones we chose. And then, yeah, you can see some examples of this. This being the original image, we can blur it slightly, or we can add different salt noise. The use case that we're looking at here is image classification. So this is a satellite. The Eurosat dataset is a satellite image dataset. It has these 256 by 256 pixel patches collected from the Sentinel-2 satellite platform. There's 10 different land use classes, so the examples are shown here. And then we're using the dataset as provided by Hugging Face. The original test data set is about 2,700 images, and we use the smaller subsample of that to make it more computationally efficient to do our experiments. Yeah, so these are the first results. So we pulled down two Hugging Face models that were pre-trained on the Eurosat data, a convex model, which is a more traditional convolutional neural network, and this swim model, which is based on the transformer architecture. So we wanted to look at two different architectures trained on the same data. And here we're showing the model performance as a function of the two different types of perturbation. So Gaussian blur here, or the salt noise. And you can see that in here, this is increasing strength of the perturbation. So for Gaussian blur, that's the size of the kernel with which you're blurring the image. And the salt noise is the amount of noise that's being added in terms of the fraction of pixels. And here we can see that both models, they start off relatively similar performance, around that 97% accuracy or so. But as you degrade the image by increasing the amount of perturbation, they follow these different profiles. And so here the blue curve corresponds to the swim model. It's more robust, because you see this rightward shift where it maintains higher performance at the same perturbation level. And this kind of points to the need to do this kind of robustness testing. Because if you were going to choose one model just based on the accuracy on the clean data, you wouldn't see this effect. You would see that both models are relatively comparable. But only when you do this robustness testing, you can see there's a difference between the two models. And then, so that was kind of the raw model performance. We also wanted to look at the explainability aspect. So if we apply a saliency map algorithm, which shows you which features the model focused on, what does that reveal qualitatively. So here, to orient you, the figure here on the left, this is for the Gaussian perturbation. Here on the right, this is for the salt noise. The first row is the original image. As we go down, the strength of the perturbation increases. And then here we show the saliency maps for the two different models. So on the left, the swim model, the convex model is the same across these two groups. And then we also show the saliency map relative to either the ground truth class of the image or the predicted class. So when these are the same, when the model makes a correct prediction, the saliency maps are the same. But there are some times where, due to the increasing perturbation, the model predicts incorrectly, and so the saliency maps would differ here. So qualitatively, we see for the swim model, which is the more robust model, the saliency maps seem to indicate that it focuses attention on this road feature, which is necessary to classify this higher class. But we see with the less robust model, the convex model, the majority of the saliency kind of shifts away as you increase the perturbation. So this is some kind of preliminary qualitative evidence that saliency, this explanation, could help indicate which models are more robust. We also wanted to do some more quantitative analyses. So we looked at both model confidence as a function of perturbation strength, and then we also computed several metrics on top of the saliency maps. So here on the top, again, convex model on the left, swim model on the right, we're looking at the class-wise model confidence, predicted model confidence of the ground truth class as a function of perturbation strength. So in general, as you increase the perturbation strength, model confidence decreases, which makes sense. The model is more likely to get the incorrect prediction there. But we see that there's differences between the two models. With the swim model, this degradation in model confidence being more gradual, which also indicates it's more robust. And in terms of the saliency metrics, we looked at 3 different metrics. Entropy is a referenceless metric, so we give it the saliency map, we compute the entropy of the saliency map. Both the sum squared distance and the normalized correlation, they are comparing the perturbed saliency map to the saliency map computed on the perturbed image versus the original saliency map. And so here, sum squared distance increases as the images get perturbed. So that's shown in the orange here. And then the correlation decreases. So it's perfectly correlated when it's the same saliency map. But as you perturb, you also see that the correlation decreases.
2 minutes.
And then the final thing that we did was we wanted to look at a correlation analysis. So for each perturbation level, we correlated the model confidence values with the different saliency metrics. And so the thing here you can see, for example, for the distance metric, model confidence is anti-correlated with that. So there's a negative correlation here. As the model confidence decreases, the distance with the original saliency map increases. And you see that there's different trends for the 2 models. So there's an increasing negative correlation here that weakens as you get stronger correlation. And then similarly, when you look at the correlation metric here, model confidence and the correlation metric are positively correlated. As model confidence decreases, the correlation also decreases. And you see again, there's differences between the 2 models. So this may be one way to start using the saliency metrics in a more quantitative way to predict how robust the modeling under different conditions. Okay, so as a high-level summary, we leveraged 2 open-source tools, NRDK and XAIDK, to create this new combined natural robustness explanation generation, custom validation workflow. We showed these results on satellite image classification use case. We performed both qualitative and quantitative saliency map analyses, and then we also did a correlation analysis to look at how model confidence is related to the saliency map quality changes. And then just at a very high level, one of the things that we think conceptually is useful here is that here is the standard testing evaluation workflow. Given an AI system, in a data set, you might pass it through, compute metrics. We think this can be augmented by including explanation as part of that as well. And for example, tracking how explanations change as maybe the data set changes or the model gets retrained. So we think this is a valuable way that explainability can offer additional analysis for testing evaluation. And then just to close, the 2 tools are open source, and so we have both different applications that you can use to test it. There's an NRTK Explorer app, which allows you to explore data sets, apply perturbations, measure model performance. And then we also have an XAIDK app that allows you to upload your image, generate saliency map explanations. So with that, I'll be done. Any questions?
We've got time for maybe one question.
Yeah, go ahead.
I have a very silly question. I probably missed it, but how do you extract model confidence values in the classification?
Yeah, so model confidence is more or less, the model sees an image, there's training classes, you assign some logic probability to each of those
Okay,
classes.
so it's based
we're
on
just
that.
taking that. Yeah.
Perfect, thank you.
Yeah.
So you may have said about it. Do you have to find any trade-off between the robustness of these models and the performance when there are no perturbations? I mean, in general, this is an issue.
Yeah, I mean, like if you're, for example, trying to optimize for a more robust model, you might trade off accuracy on the cleaning data because you want to be more robust to those. We didn't look at that specifically. We took a pre-trained model that was only trained on the original data set, and then we were evaluating robustness as we added and perturbed the original data set. But I imagine, there might be some interesting.
Okay. And last one.
Yeah.
So to generate the saliency map, do you need to iteratively perturb the input, or you just perturb once?
Yeah, so again, there are different saliency algorithms. We use the black box approach, which effectively masks the image. You're looking at the prediction, and then you do a weighted average on the mask. Just the influence stuff. But the framework is agnostic, so we could have used another saliency algorithm. It's more or less relating the explanation with the robustness test. So it's a framework. It's specifically here we use some masking saliency algorithm, but it could have been a different algorithm.
Good, thank you.